What's up, guys? Welcome back to Math 18A College Algebra. Today we are doing Chapter 4. Specifically, we're jumping into 4.1, which is inverse functions, which, funnily enough, was the lecture that I had to give as part of my TA interview. So you could say that I'm a bit of an expert on this subject. So let's get right into it. Okay, so the exercise that I had you guys do as a warm-up for a Tuesday class was find two functions, f and g, such that f of g equals x and g of f equals x as well. And so that was my way of introducing you guys to this concept of inverse functions. So we can read the definition right here. Let f and g be two functions such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. And under these conditions, you say that g is the inverse function of f. And the way we denote the inverse, f inverse, is f to the negative 1. Just be careful that you don't mix it up with 1 over f, like a negative exponent. These are not the same. This one is f inverse, and this is something else. This is just 1 over f here. And so there's another thing that we do need to be careful about when you're dealing with inverse functions, and that's the domains of this f and this g. So remember when we talked about functions, like from one set to another, from x to y, you could say? You could have f take you from x to y, and f inverse takes you backwards from y to x. And so when we had functions before, there were some properties that we had. You could have some elements in y not have an element in x that it was mapped to. But in this case, you need to have that the range of f is the domain of f inverse. So there has to be like a one-to-one correspondence essentially here. Most of the time we'll be working with functions where you don't have to worry about this part too much. But when we get into things like square roots, that's kind of the only time you want to be really careful about it. But for the most part, you're safe just working with what we're going to give you. So for the exercise I gave you guys, I said find two functions, f and g, such that f of g equals x and g of f equals x. And I'd be really interested to hear how you guys thought about this, to figure out what your functions were. But if it were me doing it for the first time, I would think I would start with some f, probably just whatever you want, really. Let's say I had like x squared plus 1 or something. Maybe I like parabolas. And then I want to find some g that when I take the composition, it gets me back to x. And so I'm thinking like, what function like undoes the operations that f does? Like f, I guess. And I'm sure you guys are thinking something along those lines when you came up with your functions. So when you see a square root, or a squared, like x squared, you're probably thinking, well, I need to get back to x, so I'm going to have to take some kind of a square root. So g is going to have a square root in it somewhere. And then I also have this plus 1, so I'll probably need to take away 1. So let's see what happens if I just do square root x and then minus 1. And then we try the composition and see if it works. So I'm plugging in g of x into f of x. So instead of the x here, I'm plugging in x minus 1. And then I'm squaring it, adding 1. The squaring undoes your square root. So this part just becomes x minus 1. And then I have plus 1. So that does give me, in fact, x, which is what I wanted. And then we have to check that it works the other way as well. So checking that g of f of x also gives me x. So g of f of x is, instead of x, I'm plugging in this f of x here, so square root of, instead of x, I put x squared plus 1, and then minus 1. So I can drop these parentheses, there's no exponent or anything that I have to deal with. So I end up with this plus 1 and this minus 1 cancel out, I get square root of x. And often we wanted to be careful when we took square roots because of the plus or minus, right? So here we're going to just need to take the positive x in order for this to work. So that's a case where you do want to be careful with your domain. And we'll take a closer look at that in 1 second here. So let's go ahead and take a closer look at the domains and ranges of our f and g. So f of x was x squared plus 1, and g of x was square root x minus 1. Right, okay. So first let's look at the domains. Well, this is just a parabola. I'm not dividing by x, I'm not square rooting anything, so my domain here is going to be all real numbers. But for g, I am taking a square root. So I need the inside of this root to be positive or 0, so greater than or equal to 0. And then by adding the 1 to the other side, I can see that I need my x to be greater than or equal to 1. So that would be your domain for this g of x here. So currently these aren't the same, but we needed to look at the range as well. So let's take a look at the range of f of x. Let's see, what's the best way to do that? So I always just think graphically, because that's kind of what I'm used to. So remember that parabolas either open upward or downward based on the sign. This is a positive sign. So I'm going to have an upward opening parabola. And then the only other thing to notice would be you can easily pick off the y-intercept here by plugging in x equal to 0. And so you can see that your y-intercept has to be at 1. So you can plot that. That's where your graph intersects the y-axis. And then it has to be symmetric about that point there. So it's going to be something like this. And this one goes up to infinity on both sides. So the range of this function, remember the range is all of the y values that my function takes on. That's actually, I guess you could say y greater than or equal to 1, right? This never gets less than 1. There's nothing in my graph down here. It's everything greater than or equal to 1. And then let's take a look at the range of this square root function. Again, I'll just graph it quickly. We remember the basic shapes of these. And so we remember what square root of x looks like. That was one of the common graphs that we want to remember. Looks like this. And then this minus 1 shifts my graph horizontally, right? Remember horizontal vertical shifts? This is going to shift it to the right by 1. Right, and you can think about that like, if I plug in 1 for x, I'm at 0, right? So plugging in 1 for x should give me a value of y equal to 0. And then from here, it just looks the same as regular square root of x. Right? So you can see that this graph never goes below 0. And It's a slow growing graph, but it does go to infinity eventually. So the range for this graph is y greater than or equal to 0. It just never becomes negative, but it will extend all the way to positive infinity. And so remember that we wanted this domain here to match with the range. The domain of f has to match with the range of f inverse, and the domain of f inverse has to match with the range of f. It goes both ways. And so this domain and this range actually match up. They're both greater than or equal to 1, so that's fine. But the domain here is all real numbers, whereas the range here is only greater than or equal to 0. And so what I'm going to have to do is actually just restrict the domain of my f here. So let me show you how that will work. Your f of x was x squared plus 1, and our, you can call it f inverse now. We found the function that is the inverse, so x minus 1. And here we're only going to want to take this positive x, like 0 to infinity, just so that we can get these two to match up. And you can check that you got the right functions by sketching a quick graph, which I actually already did, of both of them, right? So we know what they look like. But for this one, I sketched this for all real numbers, but we just want to sketch it for the restricted domain, this x greater than or equal to 0. So x greater than or equal to 0 is everything to the right of 0, right? So at 0, this was 1, and we saw that it goes like this. It's a parabola. I'm only taking the right side this time. And then this one we graphed before, it was a square root shifted to the right by 1. So just like this. And if you graph your f and your f inverse, they should be symmetric, like over this line, y equals x. Which I didn't draw them perfectly, but if you like reflect over this line, you should get the same thing. And that's how you know that they are inverses. And so then notice if I took this side as well, and I reflected it, I'd have another piece over here that I don't have. So we want to not include that in our domain. So I now want to introduce the horizontal line test, which is a lot like the vertical line test that we have for functions. But here, let's read it right here. A function f has an inverse if and only if no horizontal line intersects the graph of f at more than one point. So again, if you look at the graph of your function, we can take the one that we were looking at, this x squared plus 1. And if we take the whole domain, you can see that if we draw a horizontal line at almost any point, it's going to touch the graph at 2 distinct points, right? Not just one. So currently, this function doesn't have an inverse. But if we restrict the domain like we did, well then certainly we can now draw horizontal lines through this graph, and it'll only touch at one point. So that's an easy way to make kind of a non-invertible function into one just by restricting its domain. And we call that property of having an inverse one-to-one. We would say that the function is one-to-one. Okay, but now that we've seen this way, I'll show you a more straightforward approach. There is an algorithm that will find the inverse function given whatever function that you're starting with. So finding an inverse function. So you're starting with some f of x. So in your equation, f of x equals whatever. replace f of x with y, which I kind of did before when we were doing completing the square, and it's just because it's easier to work with a variable y rather than f of x. So that'll be your first step. Next, you want to swap x and y in your equation. Then you're going to want to solve this new equation for y. And then you're going to want to replace y with f inverse of x. And then finally, you want to check your work, just to make sure you did everything correctly. Check work by finding the compositions, right? If you find f of g, or not f of g, f of like f inverse should equal x, and the reverse as well, f inverse of f should be x. So let's now apply our algorithm and find f inverse given some f of x function here, and this is a past final problem, so you know how it goes. Good to know. So first step is to replace f of x with y. So let's do that. Instead of f of x, I will write y equals 5 minus 2x. Second step is to swap x and y. So instead of y, it's now x, and then where x was, I'm going to put y. Then we want to solve for y in this new equation here. So I can take my 5 over, subtract that, x minus 5, and then cancels on this side, so I have equals negative 2y. Divide by this negative 2. And it's fine to just leave it like this. I might pull the negative out of the denominator just because it doesn't look as nice. So then this would be y. And then next I want to replace y with f inverse. So I'll also switch the order. Write my f inverse of x first equals negative x minus 5 over 2. And then we'll just want to check our work to make sure that we got the right answer. So f of f inverse of x is going to give me, so let's take it one step further, f of f inverse of x equals, my f was 5 minus 2x. Instead of x, I'm plugging in f inverse of x, right? So 5 minus 2 times f inverse is this whole thing right here, negative x minus 5 over 2. So negative x minus 5 over 2. These 2's will cancel out right away, which is nice. So I don't have to deal with my denominator anymore. So 5 minus minus is going to become plus x minus 5. And then you can see that as we remove the parentheses, I have a positive 5, I have a minus 5 here, so those are going to cancel with each other. And I'm left with x. So going forward, f of f inverse works. We'll want to try the other way just to make sure that it works both ways. F inverse of f is f inverse evaluated at f of x, which then my f inverse was this part, right? So negative, instead of x, I'll be writing f of x. And then let's plug in our f of x. So f of x was 5 minus 2x, right? Yeah. So 5 minus 2x. And then I have this minus 5 over here too. So again, this 5, this is positive 5, this is negative 5, so those two should cancel out with each other. And then I'm going to have a negative times a negative here. It has to get distributed inside. So I'm going to have positive 2x over 2. This 2 and this 2 will cancel again here. So I am left with x, which means that we did it correctly. We found the inverse of f. Okay, so now I want to introduce another way of thinking about inverse functions. And this is an important concept. It does show up on the final often. And that's that if you know like the value of your function at some point, like you know that f evaluated at a equals b, then, and if you know that your function has an inverse, what taking the inverse does is swaps your x and y values. So if you know that this is true, then it must be true that f inverse of b equals a. And it's the same if you made a whole table of values. Maybe not x and y, we'll do x and f of x. If you know that like at 0, 1, and 2, this is say like 3, 4, and 5, then if you made a table of values for f inverse, you just swap these essentially. So my f of x now becomes my x. So I know values of my function at 3, 4, and 5, and those values are 0, 1, and 2. So that's another thing to understand about what taking an inverse does. So I want to look at a different example from a different final. And it says that suppose f is 1 to 1, which remember just means that we're going to have an inverse. We've already checked that out. And then it says if we know that f of 7 equals negative 3, what can we say about f inverse? Well, we know pretty much exactly two things. Because f is 1 to 1, we know that f inverse exists, first of all. And using this information that we just learned, we also know that f inverse of negative 3 has to be 7. So let's now apply that concept to a graphical example. This one's also from a final. He does a lot of different kinds of inverse function problems. So here we suppose f is the function whose graph is below. Find the value of f inverse of 1. So remember, here let me write. If we know that, or if we want to find what f inverse of 1 is, call it like a, then that means that f of a equals 1, right? And we know what f is. F is this graph right here. So we're just looking for the spot on the graph where your function is equal to 1. and that's in the y direction. So it's not done completely perfectly because I just freestyled it, but you're looking for where your function is equal to 1. And so here is where I'm looking. That's where my function is 1. And so you can see that that value occurs at x equals 0. At x equals 0, f of x equals 1, right? So that's what I was looking for. That means that f of 0 equals 1, right? So I've now found what a is. So then that also means that f inverse of 1 has to be 0, because inverses just flip your x and y's. Okay, now some of the examples in your book might ask you to verify that the functions given, f of x equals x cubed plus 6 and g of x equals cube root of x minus 6 are inverses. So if they're asking you to verify that two functions are inverses, all you have to do is check that f of g equals x and g of f equals x, just like we did in the other examples to check our work. So let's go through that quickly just to make sure we know how those work. So f of g is f evaluated at g of x, which is taking my f, and instead of x, I will plug in g of x. So g of x cubed plus 6. We'll plug in g of x at this step, the cube root of x minus 6 cubed plus 6. This cube root gets undone by the cube, the power 3's, so I'm left with x minus 6 plus 6, which is going to give me x. So f of g works. We can see that. Let's do the other way, g of f. So g evaluated at f of x equals, looking at my g of x function, plugging in f of x instead of x. And then plugging in our actual f of x function, so x cubed plus 6 minus 6, all under the square root, or the cube root rather. So then this plus 6 cancels with the minus 6 once again, and I'm left with the cube root of x cubed, which is just x. And remember, we're taking a cube root here, so we don't have that problem that we have when we're doing square roots, because cubics look something like this. So you're going to pass the horizontal line test no matter where you are on the graph, right? So this verifies that f and g are in fact inverse functions of each other. Okay, and I will end this lecture with an application. I had to write one for my job interview, so we're going to do one here too. So suppose Alana is addicted to a game, World of Mathcraft, so I don't get copyright strike. She paid $60 for the new expansion, Inverse Lands, and $15 each month for the subscription. If Alana decides she doesn't want to spend more than $150 on this game, how many months can she afford to play? Okay, so we're going to be using inverse functions here to figure out how many months I can play, because we can first write a cost function. So let's do that. The cost, c of x, the amount that I spend on this game, $60 up front, right, to pay for Shadowlands, Inverse Lands, and then $15 each month. So here, x is going to be the number of months that I play for. So that's going to model the amount that I'm paying to play this game, right? And then if we take the inverse of this function, I will get a function that gives me the number of months that I can play for. So let's replace our c of x with y. we swap our x and y. So x equals 60 plus 15y. I now want to solve for y. So I'll take my 60 to the other side. X minus 60 equals 15y. Then finally I need to divide by this 15. I'll go over here. Y equals x minus 60 divided by 15. And so I'll replace my y. We can call it C inverse or we can call it something else. We can call it like m of x because m will give me the number of months that I can play for. So this function here, this takes like dollar amounts and outputs the amount of time. So outputs the months. So here I'm trying to evaluate m of $150 because that's the maximum amount that I want to spend on this game. So let's evaluate m of 150. And that's going to give me 150 minus 60 divided by 15. So 150 minus 60, that's going to give me 90. Divide that by 15. I believe, what is that? 15 times 2 is 30, so then times 4 is 60, so then times 6. So that's going to give me 6 months. That's not bad. And so just looking back quickly at the function that I started with, this c of x equals 60 plus 15x. C is a function of months, right? Because I defined my variable x to be the number of months. So if you're thinking like the sets that you're mapping from, like a and b or x and y, I guess I'll call it x and y since that's what I called it in this video. This is months, that's what I defined my x to be. And then c will take me to a cost, right? Some like dollar amount. So then when we found the inverse, C inverse, which we called m, that takes my dollar amount and maps me back to months, how many months I'm going to get out of a particular amount of money. So if you're thinking about like writing an inverse function for an application, you want to keep in mind your variables and the sets that you're going to and from.